Hello student, hi, good evening. So today we are going to discuss about EK space diagram for gallium arsenide and silicon, means for compound semiconductor and what elemental semiconductor like silicon, okay, like silicon, and compound semiconductor like gallium arsenide, okay. So for that we are going to discuss what energy versus momentum diagram, that is ek space diagram, okay. So ek space diagram, let us see here. Ek, this is what ek space, ek space diagram, ek space diagram for ek space diagram for gallium arsenide, gallium arsenide and silicon, okay. Gallium arsenide and silicon, okay. ek space diagram for gallium arsenide and silicon. First we will see ek diagram, ek diagram for gallium arsenide, for gallium arsenide, okay. So first we will see for gallium arsenide ek space diagram. What is this ek space diagram? Energy versus momentum diagram. Actually it is not like a conventional band diagram that we have seen in the last class, like conduction band, valence band for insulators, to differentiate insulator, conductor and metal. So there we got the information about only energy band gap. But this ek space diagram, but if we want to explore some particular semiconductor about, let's say, electrical and optical property, so definitely for that we have to go for what? We have to go for energy versus momentum space diagram, okay. So because this what ek space diagram will tell us about more information than energy band gap, like from conventional band diagram. So from here we can get the information of about what, about its electrical and optical properties, okay. So that we will see how, as we know very well here, as we have seen what we have got this energy versus what ek space diagram. So we have got this, okay, ek space diagram. So this is what, this is the minimum conduction band energy, maximum valence band energy. So what are these are nothing but this is energy versus k space diagram, okay. From where we got this, we got this from what, actually the result of what, actually by solving the Schrodinger wave equation. Yes, as we have seen in case of what, in case of Kroning-Penney model equations. If you have not seen yet, just go and click this I button, and here you will get all the information about this energy versus k space diagram, ek space diagram for what, for gallium arsenide, for semiconductor, okay. So you can get all the information here, okay. Just click on I button, okay. So go to Cronin-Penney model equation. So there you will see all the details how we are getting this. This is nothing but this curve is what, these are nothing but these are the, and these are what, wave function, what, wave function. From where we are getting this we are getting from where, we are getting this from the solutions of what, Schrodinger wave equation, with the help of Bloch theorem. We have solved that equations. Then after solving that equation, we have got this. Okay, so these are the wave functions corresponding to what, corresponding to allowed energy band. Okay, so allowed energy band. These are the wave function. Okay, so this means what, they here particle behaving like a wave function. Particle behaving like a wave function which has both energy as well as momentum, for free particles, okay. So this we have got from this Cronin-Penney model equations, which is what, original formations of what, which shows the original formation of allowed energy band, how actually the allowed energy band form, that we have seen in Cronin-Penney model equation, that this we have obtained from there, okay. So just you go there and you will get proper concept of about this, from where it has came. Then it is what near the bottom of the conduction band, and this is what AC, and this is what EV. This is what EV. Okay, so this is AK space diagram. If you see properly, okay, so in proper manner, if you see this here, here EK space diagram, energy versus K space diagram. Okay, so here this is my zero. Okay, so here it will start like this and this. Okay, so this is for what, this is my, let us say this is 1 1 2 3, and this is my what, this is energy in what, electron volt. Okay, so and here, mm, so this is 0. So this is for what, conduction band. Okay, conduction band or gallium arsenide, okay, so and this level, this is actually at 2, it is starting at somewhere 2, from 2, and this gap is here 0.31 electron volt. Okay, so for valence band, if you see valence band, this will, this maxima occur at this point. Okay, so this is what is the maxima that occur in case of valence band. Okay, so this is what EK space diagram for gallium arsenide. Gallium arsenide. So both are occurring at same value of K. So this is K, and this is my K value like pi by A, and this may be here minus pi by A. Okay, so we are actually it is a wave function, like this is like wave function like this, this wave function. Okay, so this wave function, then we are what, we are actually limiting ourselves within one period. Okay, so this is something like this wave function, that is this we are, because for this we are limiting ourselves within one period. This is pi by A minus pi by A2 plus pi by A. Okay, so here A is nothing but it is the interatomic distance, so it is interatomic space distance. Okay, minus pi by A2 plus pi by A. This is general, this is actually that diagram, this is actual EK space diagram for gallium arsenide. Okay, here both what, both minimum conduction band energy and maximum valence band energy, that occur what, that occur for same value of what, K, that occur for same value of K. Okay, so if you see here in conduction band there is electron. Okay, some electrons in the conduction band is here. Okay, but here but all are what, tending to settle down, at the bottom of the conduction band. Okay, all the electrons, what, all the electrons in conduction band are tending to settle down at the bottom of the conduction band, and similarly here is hole hole in the valence band, all the hole in the valence band are tending to accumulate at the uppermost level of the conduction band energy, and all the electron in the conduction band are tending to settle down at the bottom of the conduction band energy. Therefore, both this minimum conduction band energy and maximum valence band energy both occur for the same value of K, that is K is equal to what, 0. That is K is equal to 0. Okay, so this is what EK space diagram for gallium arsenide. EK space diagram for gallium arsenide. This is my conduction band and this is my valence band. Okay, so valence band. Both you should what, you should limit yourself within one period, that is minus pi by A2 plus pi by A. Okay, so this K varies from minus pi by A2 plus pi by A, and hence what we are observing here, they both have direct nature. Okay, they both have direct nature. So therefore minimum conduction band energy and maximum valence band energy both occur for the same value of K. So therefore this type of material, the material which has this direct nature, okay, the material which has this direct nature are called Okay, so direct nature are called as what? Direct band gaps, direct band gap material. Okay, so these are called as direct band gap material. So these are direct what? Direct band gap, direct band gap material. Okay, these are direct band gap material. Okay, material. The material which has direct nature. Direct nature in the sense means both conduction, minimum conduction band energy, maximum valence band energy occur for the same value of K is known as direct band gap material. Okay, direct band gap material, and we see here further. Let us see further. So this is EK space diagram. This is what EK space diagram for gallium arsenide. This is general EK space diagram that we obtained from the Cronin-Payne model equations during the formation of energy band. Okay, during the formation of energy. So these are the wave function corresponding to that allowed energy. Okay, so this is EK space diagram, actual EK space diagram. Okay, so now see here what we are going to observe here. See, in case of what? In case of gallium arsenide. In case of gallium arsenide, which is a compound semiconductor, and also we have seen that they have direct nature, means they are direct band gap semiconductor material. So therefore, here the transition. If you see here the transition, what the transition? Transition is the transition of electron. Is the transition of electron between transition of electron between conduction band and valence band. Conduction band and valence band occur what occur without change, without changing in the crystal momentum, in without changing in the crystal without changing in the crystal momentum. Yes, crystal momentum, without changing in the crystal momentum. Okay, so this is what in case of gallium arsenide, which has direct nature, is known as direct band gap semiconductor material, where the transition of electron between the conduction band and valence band occur without changing in the crystal momentum. So there is no change in the crystal momentum. So therefore, their momentum is conserved. Okay, so in this case, you see here the momentum is what conserved, perfectly conserved. Here momentum is conserved. If you see here, the momentum is conserved. Momentum is conserved. So these are electrons. Okay, so these are holes. If you see here, momentum is conserved. Here momentum is conserved. Okay, because they are both direct nature. Okay, so if you see individually, so this is see this EC, this is EV, K energy, electron volt, both have direct nature. Means there is what their momentum is conserved, energy is also conserved. Okay, so energy is what also conserved. In this case, energy is also conserved. Now what happen when during transition. Okay, so during the transition, so this is what valence band. So let us say this is my conduction band and this is my valence band, conduction band, valence band. Okay, so when the electron, this is what, let us say electron. Okay, electron in the conduction band, electron in conduction band. Okay, so this is my valence band here is 4. So during transition, what happens? The momentum is conserved and energy is also conserved. Energy conserved means during the recombination of electrons and hole, this the energy that will get dissipated, energy will not get dissipated. So energy will come out in the form of photon. What photon? Photon in the sense means energy is properly conserved. It is not consumed. Okay, energy is not consumed, but it is what conserved. It is conserved in the form of what? Photon. Photon means how much? Hν. Okay, Hν. So let us say this energy band gap is Eg. So how much? Hν. Hν is equal to what? Eg. Eg. Okay. So this energy has got what? Has got radiated. This energy, which is what? Which is what? Radiated. This energy is radiated. It is radiated, not non-radiated. It is radiated form. Okay. So energy we are getting in the form of photon. Means energy has properly conserved. here both momentum and energy are both momentum and energy has been conserved in case of direct band gap semiconductor material. Direct band gap semiconductor material like gallium arsenide, because both have direct nature. So therefore this direct nature has significant effect on what? This direct nature has significant effect. If you see here, the direct nature has significant effect on what? Significant effect. So therefore what? This direct this direct nature this direct nature has what? Has significant effect. This direct nature has significant effect on what? On optical property on of optical property of the material. Okay, so optical property of the material. So this is what? This direct nature has significant effect on optical property of the material, and hence we can say that gallium arsenide. So therefore gallium arsenide and other direct direct. Okay, so gallium arsenide and other direct band gap material other direct band gap material is ideally what is ideally okay, so is ideally suitable for use in semiconductor use in semiconductor use in semiconductor laser laser okay, semiconductor laser and other optical optical device. Okay, so these are what? Gallium arsenide and other direct band gap material is ideally suitable for use in semiconductor laser and other optical device. Okay, so this is what advantages that we see in direct band gap semiconductor material, which are ideally suitable for semiconductor laser and other optical devices. Okay, so these are all about ek space diagram for what? For gallium arsenide. Okay, so everything we have seen here. During the transition of electron between conduction band and valence band, there is no crystal momentum, means crystal momentum is zero. Okay, without changing in the crystal momentum, there is a transition of electron between the conduction band and valence band. And because of direct nature, here both energy and momentum has been conserved. Okay, has been conserved. Then during the electron hole pair what? Recombination. During the electron hole pair recombination, the energy that will radiate. Okay, that will radiate it in the form of what? In the form of photon. Okay, it will not consume. Okay, so energy is also conserved in the form of what? Photon. Okay, in the form of photon, which is equal to h nu is equal to what? Energy band gap. Okay, energy band gap. This is all about what? All about the ek space diagram for gallium arsenide. Now we